Hello, today I was going to try a different way of delivering the lecture. So, uh, we are embarking on a new chapter. It's chapter 5. Um, in chapter 5, we have uh, something called driven system, the driven harmonic oscillator. You encounter harmonic oscillator in which you had a block. That's my system, right? This was the system of mass m, and it had some restoring force on it through spring. So if the block was here at equilibrium, if this guy was over here at equilibrium, and distance x is pulled this spin delta x, so it had a force kx pointed in that direction, right? So this is the system, and then we said, okay, what if this system was in a fluid and subject to viscous force? Then there will be another force from this fluid, and that's a bx dot. So we studied these systems with just this force and that force. Now you know that this system will damp out to equilibrium at some point, right? No matter how we got started. But normally we would want the system to have some motion for a long periods of time. So for that, it's required that you drive a force, or you need a driving force to continue the motion. Driving force, you can have many types of driving force, but the one that we want to study, which mathematically can help us study arbitrary driving force. All right, we would we'll show that you can study arbitrary functions by studying just cosine or sine functions in future. Okay, so we will assume that in this system you have one more force. We'll just say driving force, which is a function of time, and we'll pick a particular function of time. So this is the x direction, so this we're looking at the x component of this force. So f0 cosine omega t. Okay, so we'll use this force, which does not depend on, unlike these other forces, these depends on x, this depends on x, but this one is independent of x. So this is independent of system. Okay, so system is x. This x variable is telling me what the system is. All right. So equational motion for this driven oscillator looks like mx double dot plus bx dot. Dot is equals to d dt. Can you remember? And this shorthand way of writing that, plus kx. So these are coming from the force on the other side. You might say, okay, don't write like that, okay? Maybe write in a two-step. All right, so we do two-step writing. So mass times acceleration is equal to minus kx minus bx dot plus this force f0 cosine omega t. Okay, or we can bring all these things that depend on the system on the left side, then we just leave the driving part on the right side. So mx double dot plus bx dot plus kx. We write it like this because we want dot to be sequential and nice to see it that way. We can divide by m. Everybody divide by m. And can call this guy omega naught square. We used to call it omega square, but because we have another frequency here, we'll call this omega naught square. I'm sorry, this is the omega naught square, and this one we'll call it gamma. Okay. So we have x double dot plus gamma x dot plus omega naught square equals f0 over m cosine omega t. Solution of this equation should answer questions like how does x depend on the driving frequency? The question may be what happens at different driving frequencies? Meaning, as I change this omega, it does not depend on the system, so I can change these things and ask what happens to my system, what happens to x, what happens to energy in x, what happens, how quickly the system is damping or not damping, or what happens over a long period of time. Okay, so the questions like that can be answered. So answer will come from knowing what the solution is. So this equation, so from solution of x, so it will look like x of t, so some function of t. How do I solve this equation? Actually, it turns out to be not that difficult, but you will have to study differential equation course later on. But here I'm just going to write the answers and worry about proving that this solution much later. So you can study from the book, right? Just some kind of argument that may help you. If you want to produce cosine omega t, and here's a function of time. You're taking a function itself and taking first derivative, second derivative, and as a result of all of that, you're supposed to produce cosine omega t. You can't produce this unless x has cosine omega t over there. But when you take a cosine omega t, you take a derivative, you create sine omega t. So the best thing you can do is x is equal to some constant, let's call AC cosine omega t, something I don't know yet, and something that goes with sine omega t. So this has the fighting chance of, if I plug this in here, I will have cosine omega t and sine omega t terms, right? And so that equation can be solved, right? Or I could just say, instead of having two terms, I can have one term, and I just can be omega t minus delta. So just phase here is written as minus delta usually. It's called phase lag. Right? So let's see what overall argument is. What I'm going to get when I plug this or this in there, this or this, let's say on the left side, so when I put in here to figure out what kind of these I might need so that this is solvable, I'm going to get some constants times cosine omega t. I'm going to generate on the left side some constant a and some constant, let's call it p and q because I already used b over there, p and q, and cosine omega t. So this is no t there, no t in here, and this is not a solution of t. Okay, so these guys are independent of t, and on the right side I have a f naught over m cosine omega t. So that's what will end up, right? If I plug any of these two guys in here and I ask what will happen, I'll end up with this. And you would see that once I end up with this, you can show that this is equal to that and this is equal to 0. This is sine omega t. This is equal to 0. So what we have, a p cosine omega t plus q sine omega t equals to some f naught over m cosine omega t. How do I prove that? I can multiply this by cosine omega t and then integrate. Then I integrate over t, 0 to 1 period, 2 pi over omega. That's 1 period of this function. So 0 to 2 pi over omega cosine omega t dt. So it turns out that when you do this integration, that gives me 0, and when you do this integration, that gives me half. So you're going to have a p times half equals f0 over m times half, so p equals f0 over m, meaning all the things that multiplied to cosine omega t here must be equal to all the things multiplied to cosine omega t here. Now you can do the same trick with the sine omega t. Multiply by this and integrate dt over 1 period, and this gives me q equal to 0. So one way to figure out what these things will be is to find out, if I put it in here, what equation results. And these equations help us nail down AC and AS, or A and phi. Okay? So let me stop here, and I'm going to continue in the next video. Okay, we will record this video using a whiteboard today. We are solving this equation for particular solution of this equation. Particular solution means that when a solution which has the information of the driving force as well. Okay, so particular solution, the general solution actually includes something additional that's also possible. It's not all solutions, all possible solutions, but particular solutions will be only a solution in which I do have information about that. Okay, so I could proceed as discussed previously as an amplitude and cosine, we'll call it elastic cosine omega t. So this, I don't know this, plus a sine omega t. And if I plug this xp in for x in here, we will need to find out what these two have to be for it to satisfy that equation fully. Alright, so this is one way, or another way to write is combine this into an amplitude and phase, and that's called this kind of solution. And usually phase, we've been writing plus phi, but we're going to write minus delta here, because what happens is, in this part of discussion of the particular solution for driving force, is we are interested in this quantity, which is the displacement, how much it lags the force. So this is called phase lag. That's why we use minus here. There's nothing wrong with this in plus phi, etc., but this is just a convention. All right. So we say we plug in this thing here, and then we expand everything. So first step is plug in. So we have to take a derivative and double derivative. Second step is open up the cosine, expand. This generates something which doesn't depend on no time, cosine omega t, plus something else times sine omega t on the left side, and on the right side you have a f0 over m times cosine omega t. There are no, this is independent of t, and this part is independent of t. Okay, you can show in this equation, you can show by multiplying by cosine omega t, you can show that this a has to be equal to f over f. If you multiply by sine omega t and integrate over a period, you can show this b equal to 0. So this just becomes a equal to f0 over m and b equal to 0. You can show. Okay, you can show this. I'm sure you can do this calculation by this one comes from first multiplying this with cosine omega t. So the way it comes out is multiply by cosine omega t is step 1, and step 2 integrate over one period. One period t will be 2 pi over omega. This comes by multiplying sine omega t and then integrate over one period. Okay, I hope you can do this step, complete it. At the end of this, what we're going to get, what you will get is, let me write the answers from the book. This A's and B's is omega naught square minus omega square times a cosine delta. This is, I'm writing these equations, plus gamma omega a sine delta equal to f0 over m. So that's one equation you're going to get. So that's the a equals f0 over m. And the other one you get is omega naught square minus omega square, a sine delta minus gamma omega a cosine delta equal to 0. Okay, this you can cross out a. So we need to figure out a and delta here, right? So that's the solution. Other things are known. So here this equation tells me tangent delta is equal to gamma omega over omega naught square minus omega square. So I got the delta. So this tells me the delta, what the phase lag is. This really, if I want to use this delta in here, I need to know cosine delta and sine delta. You'll say, oh, how about divide by cosine delta? Still you need to know cosine delta, right? So there's a really nice trick of how to get sine delta and cosine delta from here. I'm going to show you that trick. So you can think of this as it's like a P over B of a triangle, right angle triangle, where the numerator is gamma omega over here and denominator is omega naught square minus omega square, and this is the delta. So if you think that trick, if you think that way, then all you have to figure out what this will be. This will be square root of this square, so p square plus b square, right? So this is b and this is p. So interesting. So you can get sine and cosine both from here. So if I go over here, I can solve for a. So the a is completely common to both of these guys. So I put cosine delta in here from this thing and sine delta in here and divide both sides and solve for a. So sine delta is like gamma omega over this, gamma omega over square root of this square, which is omega naught square minus omega square square. A whole bunch of squares here. That's really interesting, you know. And you can get really lost in all this squaring business. Too many squares, squares of squares. You gotta keep your mind straight about it. And similarly for cosine delta t, is just omega naught square minus omega square over that square root. So when you do all of this, you can solve for a. So a is equal to f0 over m. Believe it or not, this entire thing simplifies to this, and I would recommend you to work this out. So a just becomes that, and delta just becomes that. So this is called particular solution of this equation. A general solution of this equation actually involves a full solution, so to say. General solution will be complete solution. Will be another term is also included. Okay, so I'm going to stop this video for the particular solution. We'll go over the full solution next. I want to point out that if you look at this solution, it does not have initial conditions anywhere. Everything is determined. We know A based on the constants. We know delta based on the constants. So notice that it does not know how I started the oscillator. No initial condition satisfied yet, you know. So we there's all this initial, when we were working before, you know, doing this equal to 0 solution, initial conditions were used to satisfy these guys. But here, for particular solution, I actually, all of these constants are totally fixed by how much force there was, how much mass there was, what were the frequencies, and what was the damping. So so this is not full solution. Full solution will give us a place where I can use the initial condition, and tells me how different oscillators are started a different way, how they will behave in time. Okay, so the next we're going to talk about is a full solution. Okay, we can stop here. Okay, so complete solution of our driven harmonic oscillator looks like has two types of contribution. One solves just this equal to 0, and the other one solves the whole thing. Okay, thing which solves the whole thing, XP has can be written using some amplitude and some phase, but these amplitude and phase are completely fixed by the parameters of this equation. These are the parameters of this equation, completely fixed. Once you give me those things, I know what A is and what delta is. Okay. XC, on the other hand, has these two constants which are not fixed. They depend on how I started the harmonic oscillator. Okay, so you can see that if I started the harmonic oscillator at x0 equals x0 and v0 equals v0, then so given this, okay, if I have this, then I can find C1 and C2 as we've done in other places. Okay. It's complicated and tedious, but it can be done. So if you look at solution now, this and this together, it seems like as time goes, so initially so there is a time because this solution is dying with gamma over 2. So here is a, say this is t, and here is a, so gamma over 2 is 1 over time, right? So if you look at the unit of this is, so this is 2 over gamma. So some time 2 over gamma. And gamma is, if you remember, gamma is b over m. So given b and m, there is a time here for which this can be quite meaningful. You know, this is just 1/3. If this at this time, this is 1/3, and 1/3 times whatever sequence, this could be significant, right, compared to this guy. But if I go, then there's a period. Let's see over here. This is kind of is still meaningful, but then there is a place I can say t is much greater than 2 over gamma. So I can be in this region or this region. We can say specifically what kind of solution we might expect. So over here we need full solution. So this looks very chaotic because you have a periodic solution like this and another thing which is dying. So it's a combination of the two solutions. So this looks so-called transient. Over here, when I get all the way here, xc is 0. This means xc is approximately 0. When t goes to infinity like that, okay, so this exponentially kills this guy. This is at most C1 or C2, right? Because cosine can be plus or minus 1. So this is at most C1 or C2. But what finite numbers you take, this exponential thing will kill it over here. This one does not have any decaying parts. So this continues. So over here, so it's a and has a period. This period is 2 pi over omega. This omega. And over here you might have so it's pretty very complicated here. But for long time behavior, it's very simple. So this long time behavior is also called steady steady solution. And you can see that the long-term behavior is completely determined from the driving force, right? So the driving solution, or XP, completely dominates. The frequency at which the oscillator oscillates is the frequency of the driving force. The only difference with the force is when the force is maximum, if the delta was zero, if delta was zero, then you can say when the force is maximum, X is maximum. When the force is minimum, X is minimum. If delta is pi over 2, well, then you can see that when force is maximum, X is lagging by pi over 2, right? So when the force is cosine, X is sine. So this is this interesting case, and this is completely in sync. Force maximum, X maximum. When the force maximum, X minimum. When the force minimum, X maximum. So these are interesting cases. If something is in between, you're going to get in between behavior. The force may be at peaking, but X may be somewhere in the middle of its full range. All right. We would like to, this is at 1 omega is like this. But what happens if I vary omega? Well, behavior will all be the same. Suppose I just examine steady state condition for different omega values. But we can keep, say, F0 same. I use the same force, but I vary the omega. What will happen? So that's we will discover a property called resonance, and resonance of X, and that will be next. Next, we're going to talk about it, or resonance of X. Okay, so let me stop, see how this worked. Okay, we are going to talk about resonance of amplitude. It's important to know what property, when you talk about resonance, there's a resonance of power, there's a resonance of amplitude, and there's other types of amplitude. So the amplitude, we're going to talk about the resonance of this property. We are talking about driven oscillator. This driving force is driving at frequency omega. So this is the driving frequency. And when we look at oscillator at a very long time compared to 2 over gamma, then we find that the oscillator, this X displacement from the equilibrium, actually just boils down to XP. And XP we've solved that, and you can write XP in another form also. A elastic cosine omega t plus A absorptive sine omega t. You can write like that also, or you can write it this way. And here we're using phase lag. This is called phase lag. And this is the amplitude of the oscillator. So oscillator is going between A and minus A, right? Because this just can be plus, this goes between -1 to 1. So X is going between -A to +A, so -A to +A, and the A is given by this positive number, and phase lag is given by this number. So what we say, so we want to see what A varies. A is a function of A varies at omega varies. So if you look at A as a function, you might say it's a function of a whole bunch of properties. It's a function as F0 over M as one property. It's function of omega 0, function of gamma, and function of omega. But if you look at it, M is fixed. Omega 0 is also fixed because the system, this is the system, so also fixed. This is also fixed. So only thing we could vary and see how the oscillator respond is F0 and omega. F0 is the strength, so we already know if I double F0, I expect A to double, right? If I double F0, then A will double. It's this property, varying of this oscillator frequency, that's really interesting because it's going in a complicated way down here, and I don't know if I vary omega, if I double omega, what the response will be for x, how the x will respond. So that's called a study of that leads to a phenomenon called resonance. So one way to do is just plot this A, I mean it's plot versus omega and A, and this is omega 0 and 0, both of them. So when I'm not changing that, I'm changing this guy. So when the omega is 0, you can see this is 0 and this is 0, so this is just omega. So F naught, so over here I get F naught over M, and what comes out, so M omega naught square, right? So that's when omega is 0. What's not clear is what will happen later. When omega is infinite, goes to 0 here again, because this will dominate omega to the power omega square. So and omega is going to infinite, so it's going to go to 0 wave, and in between it's like that. Actually, it goes through a peak in between, and the width of this peak actually depends on what gamma is. So we can figure out where will this peak be, right? What omega value this peak will be. We can call it omega's resonance value. We can figure out what the amplitude will be. So mind you, for each omega, you're doing one experiment, right? For each omega, you're thinking. So we had studied this before, P, and so this is T greater than 2 over gamma, this region, and in this region is going at like this. So suppose I had this omega 1, so this is going to go some A1 to minus A1. So this is at omega 1 going from A1 to minus A1. When I do it omega 2, so this is omega 2, and so it's actually got bigger when omega this also the phase changed a little bit, so frequency increased, right? So frequency also increased. So this is A2 to minus A2. So as I keep going, if I hit omega r, at omega r is going to be some maximum A max, A min, A max minus A max, and it's going to go only in this region of time. Yes, it's going to go so you can see I can get the maximum response if I use this omega over here, right? So that's an important information, because if I go beyond there, I again start to get smaller response. So we want to figure out that, and where is the maximum? Well, maximum, what value of omega will A be maximum? Well, this in a calculus, you just think about A as a function of omega, and you say, I'm going to take a derivative, set the 0 and solve that equation. But this thing is in denominator and numerator is constant. So instead of A, we look at 1 over A times F0 over M. If you square it, it's going to be omega naught square minus omega square plus gamma omega square. So wherever this guy is maximum, this whole thing is minimum, but it's the same equation. So let's call this some b omega. So max of A at min of B, right? Do you notice that? Max of A is min of B, and way less algebra, because you're going to do is derivative square roots, it's going to create another square root, and it's just nasty, all right? So let's let me do out the algebra here. It's very simple algebra to do now, because we're looking at just the inside of this. So d over you can also say, I can say omega square as x equals this poor choice. Let's call y equals to omega square. So I have a omega naught square minus y square plus gamma square y. So this is function of y, and I want to know what y that will be minimum. Df over dy equal to 0 gives me 2 omega naught square minus y times minus 1 plus gamma square. And so I bring it out here, this on the other side, 2 omega naught square minus y equals to gamma square. So 2 omega naught square minus 2y equals to gamma square. So y equals to 2 omega naught square minus gamma square over 2. And y was omega square, and this is my resonance frequency. That's the place it will happen. So resonance frequency is square root of 2 omega naught square minus gamma square over 2. I hope I didn't make any algebra mistake, but this is the gist of it. Now if you put these values in here, I'll get the maximum A that will happen. So that is, this is called resonance curve, resonance of amplitude. Now you could study how phase changes with omega also. However, you don't get a resonance curve like this when phase changes with omega, and we will talk about that in the next video.